Oh, hello guys. Welcome once again to Mosty Academy UTME and Waec 2022 examination prep. We are at magnetism, and under magnetism, the first part, we are looking into moving charges, domain, classical, and terrestrial magnets. So this video covers a quick concept and revision on what you have studied before. And if this is your first time of joining us, you can please subscribe if you find anything interesting after watching the video. So guys, let's get started. Like I always say, it is important you put down what I am going to be saying, and as well, I'll be very fast, but you have it in mind that I'll make sure that all what you need to know will be explained. Now we start. The first question, we have the name given to the characteristics behavior of substance. I think this is substance, which sets their length perpendicular to a strong magnetic field instead of in line with it is dash. Now, to understand, we are going to be taking this and explain what we call the domain of magnetism. Now, when you hear the word magnetization, it simply means the process of introducing magnetism to a body. The process of introducing magnetism itself, or let's say magnetization, just English, magnetization is the process. Magnetization is the process of introducing magnetism to a body. So basically what I'm trying to say is that when we talk about magnets, we say magnets are always bipolar. I don't want to go into too much of advanced level. I'm trying to limit it with what you have an idea of with in junior classes. So when you introduce a magnetism to a body, the process is called magnetization. And how do you do that? There are many methods in which you can actually introduce magnetism to a body. That is by stroking. Those are methods of making magnets, stroking. You understand? You can also hammer by hammering in the direction we call east-west. But for now, let me just try stroking. And sometimes stroking can be in two ways. You have a single and double stroke, which I will still talk about very soon when we get to that aspect. So when we talk about introducing magnetism to a body, we say it is magnetization. And when you actually want to magnetize a substance, or you want to introduce magnetism to a substance, there are some particular substance that shows that characteristics behavior. So this behavior, I don't want to waste time. I'm sorry. I'm being given just 45 minutes to run this video. So I wouldn't like to take much of your time, but I will always talk with respect to what is needed. Please keep it at the back of your mind. So now there are some particular material that we said they already have that kind of characteristic behavior. They have that property or that behavior that make them behave like a magnet. That is, they can easily magnetize. And when we talk about those ones, those material in which they have the characteristic behavior of being magnetized, even though there is a weak magnetic field, because we are still going to talk about field. In electric field, we said field and vector quantity. I said electric field is a force that is generated on on a unit positive star that is stationary. But in magnetism, we're talking about the amount of force generated on a moving charge. That's why I said moving charges. Charges are moving. In electric field, charges are stationary. We still talk about that when we get to magnetic effect of current and some other things you need to know. So I will just limit myself with respect to what you need to understand. So my point is, so we can now characterize the domain of magnetism, which is here, into three. There is a substance we call diamagnetism. Just keep it in mind. Shorty concept. There are substance we call ferromagnetism, or let's say para. I put ferro on the last point. The second domain definition is paramagnetism. And the third, which is very important, is the one we call ferromagnetic substance. Ferromagnetism. So these three processes or characteristics or definition that we give to magnetic property is called the domain of magnetism. There are some other things you still need to know about magnetism. I said I'll be taking it one after the other. I wouldn't want it to be too much, and I wouldn't want to go into some things as you don't need for your exam. I only want to focus on the examination stuff. So what do you call their magnetism? It's simple. They are just a kind of behavior, kind of property of substance that sets their length, or their substance that sets their length or their longer axis at right angle to the direction of magnetic fields. Always keep that in the back of your mind. So they set their length. Lengths are perpendicular. Are perpendicular. Perpendicular. Please always keep that in mind. Lengths are perpendicular to the magnetic field. For this one, they set their lengths. Lengths are parallel. I want to be fast because of time, to the magnetic field. So we are defining this property with respect to what? Magnetic field. A region whereby force is exerted on a moving charge. That is what we call magnetic field. It is symbolized by B. Like I said, I will be taking it a step at a time. So always keep that at the back of your mind. So guys, and the last one, which we also give to the definition of property, these particular ones are the one that what that ask, they are very, very, they are what? They are the one that are very, very strong. They have the tendency of actually magnetizing a body that has a weak magnetic field. So they are just those body that what easily magnetize a weak magnetic field. That is the definition I'll give to you. They easily magnetize a weak what? Magnetic field. Or they easily get themselves magnetized to a body. So keep that at the back of your mind. So now there are examples of this. In fact, in A level, we define this in terms of what we call susceptibility of magnets. Like I said, it's not needed for you. And I'm not here to come and show that you need to know this, you need to know that. I'm here to only focus on what you need to know with respect to your level. So because it's just UTM and Waec. So there are classification of substances or elements that we call ferromagnetic elements. So you can always keep that at the back of your mind. The three major ferromagnetic elements that have their temperature above the Curie point are iron, ferromagnetic substance now, steel, and nickel. Iron, steel, and this is Andy, and nickel. So I think I am able to actually let you understand what you need to know here. You know, steel is an alloy of iron chemistry way. Steel, stainless steel, contain carbon, chromium, and iron. You might have studied that in your junior classes before, or in your chemistry classes. So, by the way, I think this question has answered itself. So no need to waste my time on talking much, because if I still want to go further, there are still a lot of things I can still tell you with respect to what you have. So we take this and we take the answer to this. You can see their lengths are at right angle. Perpendicular means right angle. And the answer to that is nothing but what? Paramagnetism. No, diamagnetism. So please, this is the right answer to that question from the explanation I have given to you. The second question. Steel is more suitable for permanent magnet than iron because the former means the previous, the former dash. Now we use steel. I told you steel is an example of a ferromagnetic. Now, and because steel one, the thing is what? When you say permanent magnet, you classify magnet into two. There's what they call temporary. You can just write it down. And the other one is called a permanent magnet. Permanent magnet. Temporary magnets are also called electromagnets. Please note that they are called electromagnets. Under the topic of electromagnetic induction, you are going to have deep knowledge about that, more knowledge about that. But now let's limit it to what you need to know. Now, when you say permanent magnet, that means they are those that retain their magnetism. They retain their magnetic property, or retains their magnetism for a long time. So that is that. A little bit of history, because when we say classification, I said we have temporary and permanent. When we talk about types, they said they are what we call natural magnet and artificial magnet. In fact, in the beginning of this magnetism, which was first discovered by a man, I think about 300 or 600 BC, a man called Saxon. But like I said, all these are not needed, to be honest. Let's only focus on what you need about it. So we use, keep it in mind, for electromagnet, which is we use iron, important note, shorty concept. And for permanent magnet, we use steel. And the reason because steel is an alloy. It has the tendency to hold what magnetism for a long time. Then iron. Why you use iron as electromagnet or temporary magnet is because it can easily magnetize, and also easily demagnetize. So please keep that at the back of it. Easily magnetize and as well easily demagnetize. I think I've answered that question. Now the question is, why is steel that you are using steel for permanent magnet? Because steel retain magnetism more than iron. Steel is an alloy, so definitely it will retain more magnetism. So this is the answer to this question. Because I think we have up to 20 questions for this slide. I'm giving 45 minutes. So let me see what I can do, because we're only talking about classical terrestrial magnet and the domain of magnetism. So I don't think this should be a problem, as it is the first part. You should be able to get them. The next one, my dear students. Good, fine. The next is still on the classification and introduction to magnet. Like I said, temporary and permanent magnets, steel and what? Steel and iron. Electromagnet are also called temporary magnets. Keep that at the back of your mind, my dear students. Now, again, you can also classify or say types of magnets are natural magnets and artificial magnets. Now, most of the natural magnets we have, it's just a very good example is what they call the lodestone. You've heard about it before. As an example of natural magnet, and there are a lot of artificial magnets. So they are the ones that are man-made. Artificial is always man-made. And when you talk about that, you have Ticona, Linko, and to mention but few. So I just want you to know that you can also take magnets are classified in terms of natural and artificial. This is example of natural magnets. Because there are some pattern of school pattern question that you are going to face that we ask you about what. So as a beginner on the topic of magnetism, so these are still what you need to keep at the back of. I think this is a straightforward question. Which of the following correctly explain why soft iron is preferred to steel in electromagnet? I told you electromagnets are temporally magnet. I gave you reason. I said they easily magnetize and they easily demagnetize. So soft iron are more easily magnetized than steel. Absolutely. The soft iron are more easily demagnetized than steel. That is also correct. Soft iron retain magnetic. That is not correct. We've talked about this, and the answer to this is nothing but 1 and 2, and we pick this answer. I hope students are getting this. We move to the next question. Now, about the next question, we have the places. I hope you are here with me. The places in magnets where the resultant attractive force appear to be concentrated are called the dash. Let's understand this thing. When we talk about, I told you before, we talk about magnet, you must always keep it at the back of your mind. If I want to talk a little bit of A level now for understanding sake, just for you to understand, I said we talk about the what we call electromagnetic forces. Remember, in the field of electric field, we said electric field is force acting, force is a vector quantity, electric field is a vector quantity per unit positive charge, which is a what? It can exert force on it. We can now say the force, it can exert force on a stationary charge, electric field. F is equals to, from here you said it is equals to EQ. Now, when it comes to this, we call the magnetic field. When we relate magnetic field, we say the force on what? On a magnetic field is given according to what? On a moving charge as a product of Q, V, and B. And when we say Q, V, and B, we mean V vector and B vector. Like I told you, B is what? The relationship we give to what? Interpretation or the symbol we give to magnetic field. So the force on a magnetic field, which is the force on a moving charge, is a charge multiplied by the velocity or the speed multiplied by the magnetic field. So now this is the force exerted on electric field, and this is the force exerted in magnetic field. Now, when you talk about magnets, especially when you talk about the popular one you call bar magnet, my point here is that you cannot talk about magnet without you knowing that magnets are always frame dependent, and because they are frame dependent, Magnets are always what? Bipolar. Let me just write for what you understand from your chemistry knowledge. Bipolar. That is, they have two poles. They are always north and south pole. Just the way we interpret electric field. You know, we use electric field lines. We also use the same thing as magnetic field lines to represent the direction of what? Of magnetic field. I hope I am communicating. So this question is a very simple question because you just need to keep something in mind. When we talk about a magnet, a very good example of a magnet I will use for understanding is what you call a bar magnet. Let's listen to this, a bar magnet. Now, when you talk about bar magnets and those things, it is just a simple piece of metal. The simple piece of metal, a quick one. Just maybe in future, if I see the question, I'm just going to pass it. Wow. So now it's just a simple piece of metal in which it's what? It is bipolar. When I say bipolar, there's nothing like what? Magnets don't exist as a unipole. It never exists. In fact, the same law of Coulomb's law that you guys know in electric field for charges also exists for magnets. For example, when you have two magnets, let's say this is magnet 1 and magnet 2, that is separated by a distance of r, just like what you have studied before in your words. The same Coulomb's law says that the force acting on them is equals to what we call K, the first magnet, product of the first and the second magnet, divided by the square of the distance, just like the Coulomb's law. Then, but this K is not 1 over 4 pi epsilon naught. In this case, this K is defined in what we call permeability, and it's given as U naught over 4 pi. So always keep that at the back of your mind. And this U naught is called permeability of free space. Permeability. Permeability of free space. So always keep that in mind. So the same thing also, I'm trying to let you know that what the principle of dipole that we talk about, and when you want to talk about dipole, we're just talking about the product of force and distance between two what? Equal but opposite what? Opposite charge. That is what you call dipole. And when you define dipole, you define what you call dipole moment. I'm going into what we don't need. I'm talking about bar magnets. And about bar magnet, like I said, there exists two what? Two pole. And when you talk about the two pole, you use what? You can say we start from the north. You can start from anywhere. And what this other side is south. So what happens is what? Electric field lines always move from north to south. They move from north to south. They move from north to south. Keep that at the back of your mind. They move from north to south. And these are things you need to know. Now, the lines can never meet. That is the magnetic field lines we are talking about. This thing is hanging. Yeah, very good. I think it's back. So they always move from north to south like that. So the system just behaves like what? A magnetic dipole. You can see the arrow will now be from north to south, as you can see in this pattern. So this is the way they move. You understand? They move from north to south. So this arrow will move like this. Arrow is facing up, just like what you have studied before. North pole is always pointing outside, and south pole are always pointing inside. So keep that at the back of your mind. So this is the way we relate a bar magnet. So at this particular point here, the polarity where it is shown are called the ends of the magnet. Ends, not ends and scars in economics. We call it ends of magnet, which is also called the pole of a magnet. So important fact is for you to understand that the concentration of what? The concentration of magnets are always lying at the pole, at the end, because that is where they travel. That is where the line of force are emanating. They are being generated. I hope I am communicating. So when you talk about where the concentration of forces lie, like we said, the force on magnet is given by what? QVB. V is what? V and B are what? The cross product, which we are still going to talk about under magnetic effect of current or current carrying wire or wire carrying current in the magnetic field. So, but for now, just keep all this I'm telling you because you need to know them. They are very important. So the concentration of magnet, and I told you this line can never meet. They are used to represent magnetic field. They travels from north to south. Please note that. They don't travel from what? From but inside the what? Inside here, another important point. I think I am giving you one of the most important things you need to keep at the back of your mind. Inside the what? Inside the bar magnetic set, they travel from what? From south to north. But outside, which you see the field lines, which are said to be imaginary lines. Imaginary lines. These imaginary lines, like I said, they don't exist. They just seem to exist. So inside this line, because the way we arrange a bar magnet, another thing which is important is that they are always arranged in such a way that the poles are always what? Are always arranged adjacent on a straight line, more like a straight line to each other, so that the force at the ends are mostly what? Concentrated. They want them to always keep their magnetic property, and unlike poles always attract. So we arrange them like end to end. A south pole will follow a north pole will follow a south pole. The reason why we do that is because we always want a magnet to always have that tendency to keep its magnetism. I think you are understanding what I'm trying to say. So you always arrange a bar magnet or magnet generally in such a way so that their poles are adjacent to each other, and so that they don't lose their magnetic properties. So these are shorty concepts you need to understand. This is a bar magnet. They are solid. You can also chip them. You can make them what? You can sinter them. That is the language. So the process of what? Chipping bar magnets into what? Into powder form is called sintering. Another important point, sintering. So because that is what you need for basic level. And I'm trying to talk about everything in what? In one of the fastest possible way. All concept in quick time. So that is what we are trying to do. So we have answered this question because I said the concentration of field lines are always concentrated at the bar, at the end of the bar magnet. And at the end of the bar magnet is called the poles. So always keep that at the back of your mind, because now, very good. Now, the poles generally are the north and south, but the ends are the corner. You can see the corner of these things. So now here I'm going to talk about poles, and I'm not going to break bar because this object has poles and bar. So, but bars are, sorry, I said poles. Yes, the poles, because they are always at the poles. The poles are the extreme end. You can see the ends, which is called the poles. So please note that, not the bar, the magnet bar. So ends are also called poles. So be careful about that. So you have to be very, very careful when picking answers to questions like this. So that's that about that. Let's move on to the next slide. Yes, dear students, about the next slide, we have the diagram above shows a magnet X with its south pole move along. You can see this is the south pole. This is the method of making magnet. One of the methods of making magnet is called stroking. And this type of stroke with a single piece of mat is called single stroke. You can also have another one we call double stroke. That is when we are using two particular substance. Please note that, or two particular bar. So this is very, very simple. In single stroke, it is always simple. Now, the side here, PQ here, which is the bar, the PQ is last touched by what? By this X. And you can see what it was here was south. There's one principle I always tell students in my offline classes when you are doing this type of stuff. This single stroke always produce two dissimilar, I told you, because we always want them to keep their magnetic properties. And because of that, one thing you need to understand is what? If one end is south, the other end will be north. And if one end is north, the other will be south. They can never have the same polarity. When we say polarity, they can never have the same north. You can say north and north or south in a single stroke. So for this one, the north pole is last touched from the direction of this arrow. You can see the way the arrow is going. The arrow is going like this. So the south pole was last touched by this. So the P here will induce a polarity that is different from the one that last touched it. So south pole was last touched. It will induce a pole which is north. Like I said, the ends of the magnet of a single stroke cannot be the same. So always keep it at the back of the mind. So if this is north, this will definitely be opposite of north, which is south. So my point is, the answer to this thing is north and south, as P will be north and Q will be south. Please always keep that in mind. But if it is double stroke, you can have it as the same polarity but the ends will not be the same polarity as well. So always keep that at the back of your mind. The end of a magnet can never be the same. Please always keep at the back of your mind. The major definition of domain theory of magnetic is that magnetic material are arranged, they have several parallel lines. Always keep it at your mind. So they are always arranged in such a way that they are parallel to each other, and they are in terms of what adjacent to each other in such a way that what each of them are not going to have the same polarity. Always keep that at the back of that. They are always kept parallel to each other. That is the domain, the definition. Yeah, magnets are always kept. Keep it at the back of your mind. Excuse me. Magnets are always kept. Always kept. I hope you are hearing me. Magnets are always kept in a parallel, on like poles adjacent to each other. So that is the way we keep magnets. So we always try to make sure that what their magnetism is not lost. So by doing that, we make sure their end to ends always kept parallel to each other in such a way that unlike poles are adjacent. You can see the poles here are not the same. That is the way we arrange magnets. So always keep that at the back of your mind, my dear friend. It's very important for you to have that. Look at the next question. When a number of identical small magnets are arranged in line, they are arranged in line, the strength of the resultant magnet is dash. Look at it. I've talked about that. Strength are always concentrated at the pole, at the ends of the magnet. It's largest when they are arranged end to end. Yes, they are arranged end to end, but let's see other option. Is greater when they are arranged parallel with like poles adjacent. You can see that is what we call the domain, the definition of the domain of magnetism. So this is the answer to that. Depends only on the number. No, it's greater when magnet arranged on a wooden surface. Is no. All these are no. This would have been correct, but it is an incomplete statement. They are always greatest at the pole, and they are arranged parallel and adjacent to each other. Unlike poles are always parallel and adjacent to each other. So please keep that at the back of your mind. This is a question answer, and I think all these are still simple questions that you guys can have at the back of your mind as an idea of now introduction to magnetism. Next, guys. Good. Now we are now on classical and terrestrial magnet. Now you need to understand at different locations on the Earth's surface, the Earth's magnetic field dash. Now a quick one, because we need to understand what we call a terrestrial magnet. The Earth's magnetic field also behave like a magnet. We can write a simple note because I think you need it. The Earth's magnetic field also behave like a magnet. They also behaves like a magnet. They also have north and south pole, in which, just keep this in mind, their south pole is at northern hemisphere, good, and their north pole is at southern hemisphere. So these are shorty concepts. What I'm trying to say is that for you to understand the Earth's magnetic field, it's a combination of two types of what magnet. Now let me quickly draw, because I think you need it for the sake of those of us that it should be sphere and not circle. The diagram not drawn to scale, guys. It's not drawn to scale. So now we say we have, due to geographical reasons, we have the equator. Diagram not drawn to scale. Permit me, I'm just trying to show you something. So let's say the equator. Then we have what we call the axis of rotation. That is where it is rotating. Now I just want to show some stuff because it is needed for understanding sake. You can't just believe you know them, because if we believe you know them, we are only deceiving ourselves. So my point is now, Now, the North Pole, normally the North Pole is always pointing up and the South Pole is always pointing down. Now, in this case, it is upside down. It is not like that in the what? In the Earth's magnetic field. So it is like a complete opposite because of what geographical reasons. So one thing we need to understand is what the axis of rotation is here. So we have what we call the parts in which they rotate, because they rotate in a very, very different manner. So they move out and form their own kind of the kind of pattern, which is quite different from the normal bar magnets, the way bar magnets rotate. So my point is, now this line now that is passing through the equator, you can see now they rotate about their axis, and we call that this point, as they rotate about their point, we call that point axis of rotation. Now, important point I want to talk about, because I don't want to talk about something that is too much for you. Now, as they rotate, this is the way they rotate. They now start rotating. They start, like I said, diagram not drawn to scale. I'm just trying to bring out some important thing you might have studied before, and if not, this is the way they rotate about their axis. You can see, sorry, my hand is not that straight again. So I'm just trying to form something that will make sense. So they rotate in that manner. It should be about their axis like this. So they rotate. Now, at different places, they tend to rotate from one point to another. So the kind of magnets, they also behave like a magnet because they have north and south pole. But the only thing you have to keep in mind is that their northern pole is at the southern hemisphere and the southern pole is at the northern hemisphere. So because of this, now, as they rotate about their axis, about its axis, you know what I mean, rotating about your axis. Now, they now form a kind of another important thing which I think I still need to talk about. I can't just believe you have an idea. Maybe later in the question, you are still going to see it. It's very important to understand. Now, there is a particular instrument which generally you need to understand here, my dear student. This particular instrument is called compass needle or compass bearing, which is basically used for navigation. Compass needle or bearing. That is what we use to identify the direction of the magnetic field that is produced in the Earth's magnetic field. The Earth's magnetic field is called a terrestrial magnet. Terrestrial magnet. It's a simple question. I just need to talk about some important things that I think you still need to keep at the back of your mind, because if we don't talk about it, it will still give us issues later when we need it. Now, the pattern of this now, they have magnetic axis. They are rotating about their axis of rotation. So we bring about a point at which they rotate. Now, we define what we call the magnetic meridian. Magnetic meridian. I want to talk about compass needle. A compass needle is just like a sphere, something like this. It is just like something like this. Let me just draw it. Just permit my drawing. It is just something like diagram not drawn to scale. Let me draw better diagram, because that is not even it at all. Just something that is having two corners. It is always better when I draw with my with my hand. It is something like this. So now, when it is placed it is something that is having something like the same edge. It should be at the same position. I don't know why I'm drawing like that. And I'm it is because of the nature of the pen I'm using. I'm not using my hand to draw. So keep it at the back of your mind. There's something that looks like, please pick up this. That looks like this. That is what I'm trying to draw. Like something like a four corner, like that. So keep it at the back of your mind. So when placed in the position in any place in the Earth's magnetic field, it is used to show what? The direction. Now, when we talk about the meridian line is more or less like a vertical line, like this, in which when you now place this stuff that I just draw, which is called the compass needle, you are going to see that this particular stuff, I want to place it around it. I hope I will be able to draw something nice now. I just hope so. Just manage the way it is. Diagram not going to scale. Now, it is now inclined. This particular line now here, which is the line about the axis of rotation, is called the magnetic meridian. So it is now forming a kind of angle, which is we call theta, between this particular line, the axis of rotation. So the meridian line, this particular line we call the meridian line. For example, When you talk about Earth's magnetic field, I'm trying to give you some things that you need to keep at the back of your mind. When you talk about the Earth's magnetic field, they have different characteristics. One of their characteristics is that they have what they call the compass window, which allow us to know the direction in which the magnetic field is facing. That is one. Now, they have what we call the equator. I told you about equator, which a little bit of geography. They have what we call other magnetic elements. Then if you now want to draw their magnetic field pattern, we draw them in terms of the meridian. In fact, the meridian, when the Earth starts rotating, we see the meridian point can now be what defined in two ways. We have the magnetic what north. I'm defining meridian in terms of axis of rotation now. So we can have it in terms of the magnetic north, which we call MN, and we can have it in terms of the geographical north, which we call GN. Concept video available and derivation are available. You don't need it. You only need to keep it at the back of the mind. So there is an angle between as it's rotating about the meridian. So it can change its direction to the magnetic north and to the geographical north. So we now form an angle between the magnetic north and the geographical. So the angle between the magnetic north meridian and the geographical north meridian is now given by a definition you might have studied in junior classes we call angle of declination. Angle of declination, which is also called angle of variation. So please, because it changes from one place to another, because the Earth is rotating. The Earth is rotating from one place to another, and because they are rotating from one place to another, that is where we have different time changes at different positions. For example, in my country, the time might be different from the one in Ghana. The one in Ghana is different from the one in UK, and so on and so on, because at different places in the Earth, the Earth is rotating. So when the compass needle is brought near, the compass needle always lie in the direction of north south. That is why whenever we draw compass needle, because when I lie this one, it's always forming. It always lie in the direction of north south or south north. They always lie something like in this one. We can say lying like that. That is the way they point. So they are used to for navigation to actually know the direction of the magnetic field. So always keep that in mind. Now, in that sequence, which is, I want to bring another definition, which you also need to learn, or you might have studied in your junior classes. We define another property, which we call the angle of dip. Now, angle of dip is now defined as the angle between the Earth's magnetic field and the horizontal. Wow. Wow. I'm saying wow because my dear students are here and they're actually watching match with me. So, and it is very, very funny because what I'm saying is very, very, very like at this time. Now, let's leave that aside. We are here. And I said the angle between the magnetic north and the geographical north is angle of declination. Then we define in terms of what? When we define in terms of the line of horizontal, I'm trying to bring out quick concept because in other question, I know it will be with respect to the, I told you the magnetic they do always lie like this. So angle that lies between the Earth's magnetic field and the horizontal line is now for this angle, I try to bring out. You can see this is the compass bearing or the compass needle. Are you with me? I hope you are with me. So that angle that lies between this is now defined as angle of dip. Angle of dip. So that is the angle between the Earth's magnetic field. This particular substance, compass needle, is used to declare the field, the magnetic field. The angle between the magnetic field, because it is the direction of the compass needle, and the horizontal line. So it's called angle of dip. So definitions are important, especially for Waec students. So always keep that at the back of your mind, but it varies. It varies as well. So at the equator, we say at the equator, angle of dip is 0 degree. 0 degree at equator and 90 degree and 90 degree at the Earth's magnetic field. So it is 0 at equator. I'm talking about angle of dip. 0 degree at equator and 90 degree at the Earth's magnetic field or at the Earth's magnetic pole. Let me just write pole. At the pole, it is 90. At the equator, it is 0. I hope students get all this point. They are shorty points. So my point is always keep it at the back of your mind. In fact, this line here, well, I don't need to talk too much of concept. I just want to make it very cheap. So I told you declination angle in terms of meridian, the line about the axis of rotation. We define the meridian point, then the direction can be in terms of the magnetic meridian, and it can be in terms of geographical meridian. So if it is in terms of magnetic north and geographical north, we define angle of declination, which is called angle of rotation. But if it is the other way, in terms of what? The bar magnet, the compass needle or compass bearing, it is now what defined. I will define another angle equal angle of T. And that one is the angle that lies between the horizontal line and that particular what? The direction of what? Of that particular angle of what? The angle between the horizontal and the earth magnetic what? The earth magnetic field. So always keep that at the back of your mind. Shorty concept. They are very important. Line of the same dip are called isoclinic. Line of the same dip I call isoclinic. Because I think I've seen questions like that. Line of the same dip are called isoclinic. Please always keep that at the back of your mind. So I won't say more than that. So my point now, let's answer this simple question because it's very, very important to understand. Now, this simple question asks us at different location on the Earth's surface. The Earth's magnetic field is that. I have explained just now, so I don't think that should give us any problem. That is, the changes from one place to another because the Earth is rotating. Wow, I said wow again. Now, the Earth is rotating. As the Earth is rotating, always keep it at the back of the mind. The Earth's magnetic field is always having, like what I tell you, they're always having a parallel line that is pointing northward, and that is the meridian, which differentiates from the magnetic north and geographic north. And because of that, at different places on the Earth's surface, there is what we call their field is always uniform. There is a uniform field. There's a uniform field. So a terrestrial magnet produces a uniform field. I hope you are following, in which their strength, when you say strength, you know what strength means? Strength is constant. That is the magnitude. Strength is constant. That's an important point. But direction changes from one place to another. So as the Earth rotates about the axis of rotation, they always point to the direction of what? North. At that direction of north, there is a uniform field. That field makes the magnitude to be constant. And I said that makes the magnitude to be constant. Please. It makes the strength to be constant. The strength, when I say strength is constant, I mean, please. When I say strength is constant, I mean the direction. Let's keep that in mind. The direction is constant. Let's keep that in mind. Their direction is constant because they are moving about their axis of rotation, but their magnitude will change. Their magnitude changes. So that's the important point we need to keep in mind there. It's a simple question. So at different location on the Earth's surface, the Earth's magnetic field has the same in magnitude and direction is very wrong. The same in magnitude but different in direction, no. They revolve about their axis of rotation, so this makes this to be wrong. Different in magnitude and direction, no. So we have three options out. The fourth one will be correct. Different in magnitude, but different in direction. This is not also correct. Different in magnitude, but not different in direction. So this is the right answer. I think there is a typo error for that question. So, my dear students, I hope you are getting this about the introduction of magnetism and what you need to know about its domain, classical and terrestrial magnets. I'm trying to make all these things short, concise, and direct. So let's move to the next question. Now, the next one says, which of the following diagram represents the magnetic field pattern of two isolated unlike poles? Like I told you, I've talked about bar magnets. Unlike poles moves in an hemispherical manner. Bar magnet, I've talked about that. Which one looks like what I talked about? This is the answer to the question. I don't want to waste time. I said they move from north to south. I have talked about this before. So let's move to the next slide, guys. We have to be fast because we don't have all the time here. Now, which of the following statement about magnetic line of force is not correct? About magnetic line of force is not correct. Let's say a magnetic line of force is an imaginary line in which north poles of magnet will describe it is free to move. Well, it's an imaginary line. It's correct, even though there's an error in their typing here. Most the academy team, I don't know why. The next one says magnetic line of force do not cross each other. I've talked about it. You can see what I'm talking about. When you know concept, questions are very simple. Magnetic line of force are closely packed together at the neutral point. Yes, correct. Now, a neutral point, we can define a neutral point. You can write a neutral point. A neutral point is the point, let me just write because of Waec student, in which the flux density, in which, because I'm rushing, the time allotted for me is almost, in which the flux or the magnetic flux is zero. Now we define the flux as, we write it as phi is equals to the product of what? The magnetic field, which is V, multiplied by the area. Remember, when we define the flux for electric field, we said electric field times area. We also define flux. That's the combination of different lines or different magnetic field. About how to identify the position of magnetic field, we use different type of law, which we are still going to talk about, magnetic effect of current. We've talked about Fleming left-hand rule, which I don't like students using. I always teach my classroom students to use right-hand palm rule to avoid confusion. It's the best. I will still teach you, don't worry. By that time, my video this thing will be back, my camera will be back, in which you guys will be able to see me face to face, how I'm trying to dramatize. Now, the last one, which will be the answer to this question. So there will be a point as the bar magnet starts to move from one place to another. Maybe I used the previous slide illustration to show you what you need to know. At this point, now you can see it starts moving from north to south, north to south, north to south. Now there will be a point in which all the magnetic flux leave a space whereby they don't what? They are not attracting. They are not coming together. That particular point is called the neutral point. It is possible for you to have a line of force in which neutral points are more than one. So look at this one now. In this type of what? North and south. Though this type of line is not, north is always pointing out, you know that, and south is always pointing in. So, but let's take this. This is the neutral point here. This is neutral point. In this point now, this type of hemispherical field of the bar magnet, there is no neutral point. Please note that no neutral point here, no neutral point. So when you have two like poles, you have this type of pattern. So they are definitely going to be, this is the neutral point. So they cancel out each other because their movements are moving away from the center of what? Rotation. So please always keep that at the back. But for this type of situation, for a bar magnet, there exists no neutral point for unlike poles. You understand that? That is moving in an hemispherical pattern. I'm the one that says so. Keep that at the back of your mind. Now, let's move. The point where horizontal magnetic density is zero, I just talked about that. You can see what I'm talking about. It is called what? The neutral point, NP. So this is the answer to that. No need of wasting time. We move to the next slide. Fine. The next question says, the angle between the magnetic meridian and the geograph, you can see, my dear student, I have defined that when I was explaining the terrestrial magnet of Earth, and I call that angle of declination. So I will just look up angle of declination, which is also called angle of variation. Angle of declination is also called angle of variation. Angle of dip is also called angle of inclination. Inclination is also called angle of dip. Please keep that at the back of your mind because you need that. So this is the answer to this because we have talked about it. You can see I am not going to waste time here. I'll just move to the answer. The same thing to the next question. The next question says a magnetic needle is suspended first at the north magnetic pole. It was suspended at the pole. I hope you are following. It was first suspended at the pole. Then, are you following? And then at the point on the equator, the respective angle of the needle is what? Dash. I told you, at the magnetic pole, it is always 90 degrees. Right? I hope you are there. And at the equator, it is always what? 0 degree. So please, 0 degree at the equator, 90 degree at the magnetic pole. So the answer to this will be 90 and 0 respectively, as the angle of D varies from one place to another. I hope students are following this, and it's important if you are following, you keep down a note. Wow. The next one. Look at this. The Earth's magnetic equator passes through Jos in Nigeria. At Jos, the dash. Now, I like this type of question because it is very, very what? Simple. Earth's magnetic equator. As the Earth is rotating, the equator is rotating about its axis of rotation. I've explained that. I said at that point, at the equator, we said the angle of dip at that point is always 0. So at Jos, the angle of variation is 0. Angle of variation is 0. Now, I said something the other time. I said angle of variation is the same thing as angle of declination. Angle of inclination is the same thing as angle of dip. So don't make mistake. So this is wrong. It is not 90. Angle of dip is 0 is correct because at the equator, angle of dip is 0. Horizontal component of the Earth magnetic field is 0. Horizontal component of Earth magnetic field is 90. Please note that we just saw something that is more and less like that. I hope my students are enjoying this class, and if you are enjoying this class, let's move on to the next question. And the next question says, a magnetic needle is suspended freely at an angle of theta with the horizontal component of the Earth's magnetic field. The angle between the vertical plane through the axis of magnetic needle, you can see the angle between the vertical plane through which the axis of magnetic needle and the geographical meridian of the needle. I told you the axis of the magnetic needle is always measured in the horizontal manner. So which can move in terms of what? Meridian, geographical north, and the what? Magnetic north. So magnetic north rather first and the geographical north. So I will say the angle between the magnetic north and geographic north is called angles of declination or angles of variation. Declination is also called variation. Students, I hope you are getting this because it's important you know this. So always keep that at the back of your mind. So now, be careful about this type of question. Look at it. It was suspended at an angle of theta at the horizontal component of the Earth's magnetic field. The angle between the vertical plane, that is the axis of rotation. I told you the Earth's magnetic field, they have one particular characteristics. That is what the north pole of the equator always rotates about the axis of rotation, in which we can now form two characteristics we define in terms of angle of dip, angle of what? Angle of what? Inclination, and angle of declination. So inclination is angle of dip, angle of variation is the same thing as angle of declination. But here we have angle of declination directly. So you might pick option D, but I can tell you in A-level class, angle of variation is the same thing as angle of declination. I talked about that the other time. So please be careful, but because this question actually provides declination directly, that is why we are going for choice D. I hope you understand this, guys. I will have picked this is also because B is also correct, but you just need to be careful again because this examiner actually made mistake because angle of variation is also called angle of declination. I am telling you because I know concept. So guys, let's take the next question. That is if we still have. Good. The next question says a plotting compass is placed as a compass needle is placed near a stationary electric charge. We don't use compass needle to measure our electric charge. We only use to know the direction of a magnet. Now, a bar magnet, correct? Wire carrying electric current. Now, a wire carrying electric current behave like a magnet. Let me quickly talk on that because you need that. Now, for a wire carrying current, when you have wire carrying current, wire can carry current downward and they can carry current upward. Just note that they behave like a magnet. Now, when magnet is placed close to a wire carrying current, you can see the direction of this one is downward. Downward is south. Keep it in mind. As ion filings are brought very close to it, you are going to see what the pattern of this particular thing. They will now lie the magnet or the ion filings. Ion filings are chipped magnets or granulated magnets, anyhow you want to call it. The ion filings are going to align themselves in a concentric pattern. When I say concentric pattern, I hope students understand. They are going to form something like circle like that in a concentric manner. So these are one of the simplest concepts you can learn as a junior student now. In A-level, you still learn more about all these things. But for now, let me just give you with respect to what you need to know. So if the direction of the wire is north, the teacher will have given you a lot of principle and logic to identify the direction of what? Direction of the magnetic field. So always keep it in mind, if the direction of what? This is not, wire carrying current behave like a magnet. Please pick up this. This is not. So we say if this is south, if the direction of wire carrying current is downward, the magnetic field will move in a clockwise manner. You can see south is clockwise, CW, north is anti-clockwise. So always take that at the back of your mind. This is anti-clockwise, ACW. It's simple. A lot of law. Your teacher will say use Maxwell Cox-Clue. Some will say use right hand rule, but my own is always right hand what? Palm rule is the best. Position your wire. Now you can see that it is up here. When you put something up, put wire, just hold your pen like that. If it is facing up, you can see the direction of your tongue. Move your hand, you will see that it is moving anti-clockwise. So the direction of the field is coming to this direction. They are coming down, down, down here, and they will concentrate here. So magnetic field is at this side. So the field, magnetic field is at this side. It's at the north, south, west, east. It's concentrated at the east side. But if it is the other way, put that biro upside down. You will see the direction of your fingers, where your palm is facing. You are going to see that your palm will now face a kind of opposite to this. So it is now moving in a clockwise manner. You understand? Clockwise manner. When I say clockwise manner, you understand what I mean by clockwise. So when you say clockwise, clockwise is the hand of the clock. This is clockwise. Look at me. Here I call this one anti-clockwise. I'm moving clockwise. Everybody know clockwise, the hand of the clock. This is the hand of the clock. So this is not clockwise. Excuse me. So please always note that. So you have this will move clockwise. So what I've drawn there is wrong. This is down, down. Wow, why am I making silly mistake? Clockwise movement is like this, like a clock. So this is down, down, and this is going to be what? Up, up. So, and this is anti-clockwise. You know, anti-clockwise is movement in the opposite way. I'm very correct, but the arrow I'm showing is wrong. That's what I want to claim. They move like this. You can see down, 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 then to up, up, up. So this is the way they move. Always keep that at the back of your mind. So for up currents, the field will lie in the direction of in this direction. We say up. Just imagine yourself driving a Porsche. All these laws are too complex for me. I believe the right hand palm rule is always the best. So if your current is facing, your thumb is facing up, just hold your pen. Put your thumb, let it face up. You are going to see that the direction of the field is coming to your side. That is where your fingers is facing as you are holding the pen. Where is it facing? It is facing where you are. You can see it's facing this side, this particular side. That's where it is facing. But if you turn the Bible upside down and you turn your hand upside down, let the direction of your thumb, let it be facing down. You will see that the direction of what the magnetic field is lying in this side. We call west side. There are a lot of rules. Some people will tell you use snow rule, SNOW, and INSO-E. You can see north direction, magnetic field is over the east. In the north, if you have the north side direction, if the current is facing the north direction, then the direction of what? The direction of the magnetic field is always what? At the east side. So, but if it is moving from south to north, that is, the current is what? Is at the south. The concentration of the magnetic field is at the west. They call this one snow rule and the INSO-E rule. So anyone you want to use, but my own is always right hand palm rule is always the best. Because when you use right hand palm rule, you are not going to make mistake talking about wire current. My point is like a wire current behave like what? Like a magnet. And the way they behave like a magnet, like I tell you, if they are separated by a distance R, I've told you about that the other time. So because they are carrying different currents. Now, when wire carrying current, we say the force generator in the wire carrying current is always equals to what? The magnetic field, the current, and the length of the wire. You can keep this for now at the back of your mind because you are still in elementary class. I will not talk more than that for now because magnetic field can change direction. It's a vector quantity. So note that. So it can carry current in different direction. Then I told you your law between when you have two parallel wires, you can also have two parallel wires carrying current in the same direction. Always look at it now. When wire carrying current, parallel wire carrying current separated by a distance of R, just keep it in mind, wire carrying what? Force between wire carrying current in the same direction. When wire carrying current in the same direction, what we notice was the wire has a length of L and they are carrying the current of R. The force generated in them is always what? BIL. B is a vector quantity and the length is also vector. So always keep that in mind. So we define the magnetic field according to a man called Barrow-Savart. You may not need it for now, but I think new pattern, like I said, I told you U naught over U naught I as the first current over 2 pi R. This is the definition we give to it in A-level classes. So, but for now, You don't need that. The only thing you need is that when you have vertical wire carrying current in the same direction, they attract. So keep it in mind now, same direction for vertical wire or parallel wire, same direction, attract. Whereby opposite direction, that's the point you need to keep for opposite direction. This is direction, repel. So this is the point I want you to keep in mind, because what we notice is that this one, we are talking about the wire of the first one, they have two wire carrying currents, I1 and I2. Please note that they have L. So this we move towards this and we calculate the force generated between them. So because they are the same direction, we say they are going to attract. So for vertical wire, be careful. Does not obey your Benjamin Franklin that like poles repel, unlike poles attract. It is upside down. It is opposite of that. This is a simple question. This is just asking us about the work of a compass needle. It is used to determine the direction of magnetic field. For a magnet and a wire carrying current, I said, behave like a magnet. And this is the short way to understand that. So my point is the answer to this is Roman figure 2 and 3. And I think this is the answer. Yes, it is. And that is the answer to that question. I have used more than the allotted time. Well, the fact is I am trying to cover every aspect you need to know. And that is the joy of following us almost the academy. Now, which of the following statements is not true about magnetic field around an infinite straight wire carrying conductor? I hope you are still here. Please don't get tired. Always watch this video to the end. It is always very good for you to watch this video to the end. So we are talking about which of the following statements is not true about, it's not true, it's not a true statement about magnetic field around the infinite wire. That is parallel wire. That is what we call infinite, because one of the conditions we tell students in level classes is that if you are talking about wire carrying current, magnetic field due to what? One wire with respect to the other. It's like what the wire, one of the wire must be at what? Must be at an infinite, must be infinite, must be infinite. Please always note that. And that is even what brings us to what we call helical spring, helix, for A-level student. But for you guys, you don't need all that. Your questions are always cheap, like I always say. Let's say the line of magnetic forms are in concentric form. No, you can say when they are vertical wire, they are not in concentric form. It is not, look at it, it is, we are talking about, it's not true about, they said, which one the following, sorry, is not true. Please always keep that at the back of your mind. Which of the following is not true about wire carrying current in the same direction or whatever that you have here? One thing you need to understand is that when you have wire carrying current, I've told you, which of the following is not true? When wire carrying current are like this, when you bring the iron filings to them, what happens? They align themselves in a concentric manner. Concentric manner means they form something like a circle. Are you guys with me? Now, please always keep that at the back of that. So this first statement is true. We've talked about it. Please get that. The second statement here is that the lines lie in a plane perpendicular to the conductor. Yes. Now, Fleming left-hand rule. Let me let you know. That is what we are talking about. Now, we said force is equals to BIL. Now, if you have a position, let me just quickly let you know, this is a magnetic field. I don't want to talk about too much of concept, but this is why you need to know a teacher that knows it very well and those that are struggling with it. Now, this is a magnetic field. We always use something like this to represent them. Then we said that if a wire carrying current is brought inside the what? A magnetic field. Always keep it at the back of your mind. This is a wire carrying current upward, current I. Current is denoted by I for those who don't know. In which the magnetic field is always perpendicular. Magnetic field is a vector quantity. That is why it is inside. So the force used or generated is always equal to what? B-I-L. Whereby L is the length of the wire. So please always keep that at the back of your mind, that the force generated when the wire carrying current is placed in the what? In the magnetic field is BIL. And the magnetic field is always what? In such a way that is perpendicular to the conductor. In fact, that is why I said the best method you can use is always the right hand palm rule. When you use the right hand palm rule, it's the best. Right hand palm rule is the best. I think I have videos on that. I will link you guys to the video if you need. You can drop a comment. Now, right hand palm rule is the best method. But if you are used to Fleming left hand rule, it's also good. Your index finger, second finger, current, index finger, then thumb with what? Your thumb is the direction of motion, which is the velocity vector or whatever. Index finger, second finger, current, index finger, you know what I'm talking about. You guys, you know all this stuff. And if you don't know that, that one can be confusing when we get to electromagnetic induction. That is why I believe using the right hand palm rule. And how does the right hand palm rule work? It is very, very simple. If you need to know that, it is just a simple law that tells you that what, when you use your right hand palm rule, always keep it at the back of your mind. The first thing is the direction. The thumb, the finger will always point. Your finger will always point. Let me help you write it down. Finger will always point. Time is not on my side. Finger will always point in the direction of magnetic field. So if you point your finger now, just on what you are on my screen now, point your finger directly to the field. That's start. Point your finger directly to it. I hope your fingers are placed there. That means your hand will be directly straight. So your fingers are pointed directly to the magnetic field. As you point your finger, your four fingers, they are pointed directly to what? To that screen. That's I mean, point your finger to all these things now. Let your forefinger point straight. Look at the way your hands will be. I'm trying to do that right now. My students here can see me. Now, as you point your finger directly to the magnetic field, your thumb, you can see that the direction of your thumb is facing up. Can you see that? So your thumb is facing the direction of the current. Now, the direction of what? You can see. These are things you need to understand. Your thumb is telling you the direction of the current. Now, the current now in this thing now is upward current. So your finger, that your four fingers that is pointing to what? To the field. The four fingers are pointing to the field. That thumb is talking the direction of the wire carrying current. The current is going up. Are you there? Now, whereby your palm, you know where your palm is, the remaining part of the palm, your palm is giving you the direction of the force. Now, in this case, if I ask you, where is the force pointing? The force is pointing what? Outward, because your palm is now pointing like this. So your point, the point is what? The force is pointing what? Outside, in this case. I hope students can see. So always keep that when this arrow is facing up, force is always pointing out, and the force is always perpendicular to the field. In fact, we write it in full if it is perpendicular as BIL sin theta. So that's the derivation of all these things are available on my channel if you want to watch the full concept video. So the second point here is correct. Now we go to the third point. The third point says the strength of magnetic field depends on the wire carrying current. Yes, we already talked about that. The strength of magnetic field B depends on the what? The force, the current, and the length. You can see those are the factors that affect the strength of the field. The next one, the lines of magnetic fields are parallel to each other. When you say they are perpendicular, you can't pick they are parallel. So this is the answer to the question. So this is our answer. So let's read the last option. The magnetic flux decreases as the perpendicular distance of the conductor. I told you flux is the product of this multiplied by A. So always keep that at the back of your mind. So as the gap increases, as the gap of the magnetic line increases, the strength of the magnetic also decreases. So always keep that at the back of your mind. So let's move on to the next one. Now the last two questions for this slide, I hope students are still there with us. The last two questions is, which of the following shows the correct direction of magnetic line of force of a vertical wire XY? I told you when they will lie concentric. I told you down is clockwise, up is anti-clockwise. I can't say this. This and these are wrong. These two are wrong because they will definitely form a circle, concentric pattern. So if the arrow is facing up, you know you are going to pick something. I said downward is clockwise. So if it is down, you move clockwise. That is, this place will be down, this place will be up. Please note that. So I can't see this carefully very well. So please, if this is done, this is the way you are going to do it. So always keep that at the back of your mind anyway. So we are going to pick the correct answer. So like I said, the time is not on my side. So I think this is done. So if it is done, this one will also go down there. So downward is clockwise, upward is anti-clockwise. So keep that in mind, but this is not clear enough. But you know, it will never be like it. It's always going to be concentric pattern. I hope you understand that. So the next one. The figure above, this is the figure, shows a conductor PQ carrying a current I in the direction stroke. You can see the current is down. Downward is clockwise, clockwise, clockwise. Downward is clockwise, downward is clockwise. So we expect the wire carrying current to form something like concentric. So clockwise means down, down, then up, up, as in the arrow of clockwise. So now, The position now, the question is at a particular position near the conductor. I have spent more than the 47-minute limit. I have used 1 hour plus, so I have to rush, guys. The particular position near the conductor is a compass needle K. Okay, a compass needle was brought there. I told you the compass needle is used to throw the direction of what? Of the magnetic field. Then getting the Earth's magnetic field, okay, the compass needle will dash. Set you in any direction? No. No, it will set you in a particular direction, which is always in the north-south direction. Set you in a fixed direction only if the conductor use magnetic material. No, wire carrying current behave like a magnet. So whether it is magnetic material or not a magnetic material, it will definitely what? The compass needle shows direction of magnetic. So far there is a magnetic field, whether it's a magnetic material or not, it will definitely set you in a particular direction. So the answer to that should be choice C. So I think it's a simple question we can pick answer to. So I think that's all. Let's see if there's one more. Wow, there's one last section. Guys, the last one is a horizontal component of the Earth's magnetic field and the magnetic field of a straight wire Earth carrying current into the plane of the paper. Which of the figure correctly illustrate the resultant magnetic field pattern? There are two things. Earth's magnetic field, I told you how it behave, and a straight wire carrying conductor. A straight wire carrying conductor would behave like this. Earth's magnetic field behave like this. I told you already they behave like rotating about their axis. They start moving, they rotate. I told you the other time they rotate. Diagram not done to say, I've done that before. And if we go by that because of time, so we can say it's a combination of two fields. The wire carrying current is inside and the Earth's magnetic field is outside. So choice A is very correct to this. The last question, my dear students, sorry for 1 hour 10 minutes to what I'm using now for my calculation. I hope I didn't make mistake from that. I'm sorry, apologies to my producer. Now the last question in the figure above, QR is a vertical wire and the current I is flowing from R to Q. So you can see it is up. Upward is anti-clockwise. Upward is anti-clockwise. I told you upward is anti-clockwise. Snow rule. You can say snow rule or use that. Upward is anti-clockwise. Anti-clockwise means it will lie like this. You can say anti-clockwise means NSOE. So the concentration of the what magnetic field will lie at the east side. So if it is carrying the wire carrying current towards the north, from towards the north, the concentration will be at the east. I hope we don't make mistake there. So always keep that at the back of your mind. It is very simple to know what this for, and that is how to get the answer to this question. So the answer to this question is east, because the direction of the magnetic field will be at the east. I've explained that to you. Upward is anti-clockwise. Anti-clockwise means east. Clockwise means what? West, in the direction of what? So some people use snow rule or the east rule. So that's the answer, my dear friend. Apologies for rushing you towards the end. It's because of the time frame. So guys, this is all about the magnetism part 1, which is the first part. And next topic is electrical charge, which is according to a syllabus. I'm working with respect to the syllabus of UTME and Waec. So always keep that at the back of your mind to join us. It's a daily program. I hope you guys enjoyed this class. You can download the video as well if you wish to watch it over and over again. Don't worry, with all these concepts, you can actually score as high as 95% in your forthcoming exam. So guys, see you soon. Don't forget to subscribe if you find anything interesting. Bye for you. Thanks.